Okay, precast students, in this video we will be studying different types of models that we can use to model a given set of data. Okay, your heading for today will be mathematical modeling. If you'd please write that down in your notes today, mathematical modeling lesson 1.6, and be sure and include today's date if you would please, so that your dates or your notes are organized. Okay, you're ready for today's mathematical modeling lesson 1.6, and be sure and include today's date. Now, in Algebra 1 and Algebra 2, you actually did some modeling, okay? Let me refresh your memory. Remember, you were given 2 points, and you wrote a linear equation. When you did this, you were fitting those 2 points to a linear model, and the model that you usually used in Algebra 2, although there were others, but this is the main one that you guys used right here. Okay, alright. Also, in Algebra 2, when you were given a vertex and another point, and you wrote a quadratic equation, you were fitting those 2 points to a quadratic model, and I've not written this model for a long time, so I'm probably way off. I think it was something like y equals a x minus, boy, I don't know, h quantity squared plus k, I think is the model you should have used in Algebra 2, okay? And you were fitting those lines to a quadratic model where h and k were your vertex, and then your x and y were the other point that was given to you, and your a was a constant term. So you would find a and then write your model. Okay, so you've done mathematical modeling before. You might not remember it, or it might not have been called this, but it's the exact same thing, where you're given a formula like this model here, or you're given a formula like this model here, and you write an equation. So that's what we're going to do today, okay? Today we'll be looking at direct variation, inverse variation, joint variation, and the least squares regression with a graph. We're going to use a graph for today to learn how to use the least squares regression formula, okay? Alright, so let's go ahead and jump right into this without any hesitation. Sounds awesome, right? I'm sure it does. Let's get started. Let's first look at direct variation, okay? Direct variation. Now, basic direct variation. Understand the phrases y varies directly as x and y is directly proportional to x mean the same thing. These two phrases mean the same thing, so get used to both of these phrases when it comes to your basic direct variation. Now, why am I using the word basic? Because in a little bit here we're going to look at another type of direct variation dealing with exponents, so we're just calling this our basic direct variation, okay? Now take some really good notes. If I go too fast, just pause the video, okay? But you should understand, I would write these phrases down, because you need to know that when you see these phrases here, it's talking about direct variation, okay? Now, the model for y varies directly as x, or y is directly proportional to x, is this model right here. You need to make note of that in your notes. You are to use this model when you're dealing with your basic direct variation. Got it? Y equals kx. And we call this obviously direct variation. Now, continuing on. Let's talk about this model, y equals kx. First, understand that k is a number. It is a constant. For example, if I wrote this equation here, this would be a model or an example of direct variation. Y is y, x is x, and 2 would be your k. Alright? Second, understand that this model is a linear equation. Let me show you what I mean. Back to my other equation I just wrote for you. Is that not a linear equation right there? Sure it is. And 2 is called, well, 2 has a special name. We'll get to that in just a second right there, okay? But 2 right here is your k, but it's also your what else? Is it not your slope? Come on, guys, think of your Algebra 2 classes. Y equals mx plus b. Whenever y is by itself and you have a linear equation, the number in front of x is your slope. You say, well, Mr. Earhart, what's your b? Just 0 plus 0. Okay, so whenever you have a basic direct variation equation written like this or like this, your k is really the slope. It's the slope of a linear equation. Okay, so please understand that. Also, K is called the constant of variation or the constant of proportionality. Okay, if I've gone too fast, back it up and watch this again. Okay, so keep all that in mind, guys. When we're talking about varies directly or direct proportion, you're going to use this model here. This is a direct variation model. K is a number. Don't forget that. And K has a name. We call it the constant of variation or the constant of proportionality. And also, don't forget K in this situation here is also the slope. Don't forget that this is a linear model, okay? This is a linear equation. Your basic direct variation equation is a linear equation. Now, let's look at a problem that applies this information and kind of see how we do, okay? All right, here we go. Let me get a drink here real quick. The reason I've written page 119, example number 2, is instead of you guys copying this problem right here in your notes, you could instead just put page 119, example 2, and then you could open your books up and follow along, but you won't have to copy this whole problem down, okay? Now, there will be one problem that we do today that's not in your book, and you will have to copy that problem down. The rest are in your book, okay? So here we go. In Pennsylvania, now look at this expression right here, guys, look. Remember, we're talking about y varies directly as x, or y is directly proportional to x. Well, look at this. The state income tax is what? Directly proportional to the gross income. That's the same thing as saying y is directly proportional to x. So your state income tax is going to be your y, and your gross income would be like your x. So instead of using the model y equals kx, I'm going to change the little, and I'm going to use tax, I guess state income tax. So tax equals k. I'm going to put income for I. So instead of using y, I used a t. Instead of using x, I used I. If you want to use y and k, please feel more than welcome to do that. There's nothing wrong with that. But let's go over this again. Do you see how I knew right away we had direct variation? I saw the phrase state income tax is directly proportional to gross income. So I know this is directly proportional to this. So state income tax would be like my y, and gross income would be like my x. So there we go. So I'm going to use this model right here. T equals ki. Now let's continue on and see what we need to learn here. And I did not mean to do that. Alright, here we go. You are working in Pennsylvania, and your state income tax is $46.05. Your gross monthly income is $1,500. Find a mathematical model that gives the state income tax per month in terms of your gross income. I should say per month. Now, okay, guys, in order to find a model, I just simply have to find k. Once I know what k is, I can write my model. Okay? Well, this shouldn't be too difficult to do. They've given you a scenario that you can, quote unquote, plug into this formula and find what k is. Look, your state income tax deduction, okay? So your tax is $46.05. So for t, I'm going to put $46.05, okay? Your income is $1,500. Now, if we simply divide both sides by $1,500, you're going to get 0.0307. Now, a lot of students like to stop here and think that they're done. Well, to be honest with you, you did a great job of solving for k, but that's not all that I asked you to do. I also asked you to find a mathematical model that gives the tax in terms of the gross income. So tax comes first. Then where my k is, I put 0.0307, and then I. So there it is, guys. We're done. Is that not a mathematical model that gives the tax in terms of the income? Sure it is. Tax in terms of income means taxes by itself, and over here's your income. So you can give me an income. Maybe instead of making $1,500 per month, maybe you make $6,000 per month. That'd be a nice salary. So $6,000 per month. Put that in right here for I, and multiply it by 0.0307, and you would have your taxes for that month. Okay, so there we go. Let this sink in. See if you have any questions, guys. Pretty simple. And let's move on, okay? We wrote a mathematical model because we knew we had direct proportionality. Okay? Alright, let's move on. Now, let's continue our study of direct variation, but let's look at a different type of direct variation. So, we're still dealing with direct variation. And remember, I told you guys we were looking before at basic direct variation. Now we're going to move on to a more complex type of direct variation. Here it is. It's called direct variation. I would write this down and make note in your notes that we're switching gears now a little bit. Direct variation as an nth power. Please copy that down. Direct variation as an nth power. Direct variation as an nth power. The model looks like this. Y equals kx to the n power. So everything's still the same, students. I mean, everything is still the same. You've got your y, then your equal sign, then your k, then your x. The only small difference is now your x is going to have an exponent n. Okay? So that's the model we're going to use whenever we have direct variation as an nth power. Now, how do you know when you have this type of variation? Well, let me give you the phrases that you're going to use. You would, or not use, but you would look for. You would use this model when you have situations where y varies directly as the nth power of x. It might say y varies directly as the square of x or the cube of x. Well, that's what we're talking about. Or it might say y is directly proportional to the nth power of x. Okay? It might say something like that, and you would know then that you're to use this model here because you have direct variation, but you're dealing with a power. Direct variation, but you're dealing with a power. Okay? So again, let's look at an example. This will help, okay? We're going to give you a lot of these types today of problems, and then give you an example to go along with it. Okay? Alright, here we go. Page 120, example number 3. Please feel free to copy that in your notes, okay? I would write that down if I were you. Page 120, example 3, and that will save you copying this problem down. The problem reads, the distance a ball rolls down an inclined plane is directly, really it should say declined plane, but that's okay, is directly proportional to the square of the time that it rolls. During the first second, the ball rolls 8 feet. Okay? Model this information and then state how far the ball will roll during the first 3 seconds. Well, let's take a look at this, guys. First of all, we have to figure out what type of model we're looking at using, okay? And it says here, the distance a ball rolls is, so I've got distance is directly proportional. So, distance is directly proportional, not to x, but to the square of x, or to the square of the time. The square of the time that it rolls. So I have distance is directly proportional to the square of the time. So I'm not going to use x here. I wanted to put that. Just going to put a filler there until we put in t, but it's going to be t for time. Okay? So distance is directly proportional to the square of the time that it rolls. There it is. That's perfect. That's exactly what you want. Now, all that we have to do is find k, and then we'll have the model completely done. And that's what it says to do. Model this situation. Okay? So here we go. During the first second, so my time is 1. So during 1 second, the ball rolls 8 feet, so my distance is 8. Now let's solve for k. This should be really simple. 1 squared is 1. 1 times 1 is 1. Times k is k. So 8 equals k. Alright? So where the k is right here, I can put 8. So here's my model. T equals 8t squared. Now students, on a test or a quiz, I want you to write that down for one of your answers. Why? Because it says model this information. So you've got to write a model that models the information correctly, and that's what we've done. Next, it says to state how far the ball will roll during the first 3 seconds. So put 3 in for time. Just like that. And find the distance. Now remember, you do not take 8 times 3 first. You square your number first. So 3 squared is 9. Then take 9 times 8 and you will get 72. 72 feet, okay? So there we go. Here's the model. And then how far will the ball roll in 3 seconds? 72 feet. Now, you can use this model also the other way, students. You could also do something like this. You could say, how many seconds will it take the ball to roll? I don't know. 96 feet, okay? So, how much time will it take for the ball to roll 96 feet? So, put 96 in for the distance and solve for time, okay? Divide both sides by 8, and you'll get 12. And then take the square root of both sides, and the square root of 12 is going to be 3.46. So it's going to take 3.46 seconds for the ball to travel 96 feet. So once you get the model, you can do all kinds of things with it, okay? Alright, let's continue on. Now, there's also another type we're going to look at. Well, let's review real quick so there's no confusion, okay? So far we've looked at something called basic direct variation, okay? Then next we looked at direct variation when you have a power, okay? So direct variation as an nth power. And now we're going to take a look at inverse variation, okay? So please make note of that, inverse variation. The model for inverse variation is y equals k over x. Y equals k over x, okay? So please make note of that, write that down. So we've had 3 models so far. Y equals kx, okay? And y equals kx to the n power, okay? Whatever that power might be. Now we have a third model, and this is the model you would use. This is your basic direct variation. This is your direct variation dealing with a power, and this would be your inverse variation, okay? And so your inverse variation model, what you need to know is this right here, y equals k over x. Now, when would you use this model? When you hear a phrase, something like this, y varies inversely. I know it's misspelled. Y varies inversely as x, or y is inversely proportional to x. Those are phrases you would hear that would tell you you're going to use this model here, okay? Now, k is still called the same thing, constant of variation, constant of proportionality. However, you do understand, so let's pause and review here for a second. Remember I told you guys this was a linear model, and it is. Thus k was also your slope. That's not true with this. You do understand that, don't you, students? Because this is not a linear equation. This has a power right here, okay? And this is not a linear equation right here either. This is not a linear equation. So k is not a slope here, and k is not a slope here. It's still called your constant of variation or your constant of proportionality, okay? But the only one of these 3 that's a linear equation is this one right here, okay? Alright, let's continue on. Now, let's look at a problem that will apply this information. So I think this will make sense. Take some really good notes and pay attention. Here we go. This problem is not in your book, so you can just copy down the important information. I'm going to pause for about a minute to a minute and a half here while you guys go ahead and copy down this whole entire problem, or you might just copy down the important parts of the problem. That's up to you. Excuse me for yawning, guys. A little tired tonight. Okay, here we go. The time t. I'm going to read this while you're copying. The time t required to do a job. Look at this. Varies inversely. There's the key phrase. Varies inversely as the number of people p who work on the job. Assuming that all work at the same rate. If it takes 72 hours for 9 people to frame a house, how long will it take 12 people to complete the same job? Okay, I'm going to pause. I'm going to be quiet here. I'm just going to go ahead and wait. So go ahead and copy this problem down, and we'll go on in just a minute. equals K over X. Instead of using Y, I used T for time. Instead of using X, I used P for people. Okay, so there's my model that's going to help me find K. Now, if it takes 72 hours, that's my time. For 9 people to frame a house, that's my P. Now let's go ahead and solve for K real quick, okay? So if I take 9, if I want to solve for K, I'm going to multiply both sides by 9. So 72 times 9 will be 648. So 648 equals K. So now I can take this, substitute 648 in for K, and I should be cruising right along. T equals 648 over P. Alright, there we go. Now, how long will it take? So I'm looking for time, looking for T. Will it take 12 people to do the same job? So time equals 648 divided by 12. I have 12 people. So where the P is, I substitute 12. Okay, so let's see what we get. T equals 54. I believe I did that quickly in my head, but I'm pretty sure that's right. Okay, so there we go. So it would take 12 people 54 hours to complete the same job, and that's important to know if you're a big contractor, knowing how many people to hire, how many jobs you can get done in so many days, how many hours it will take, etc. Then this is helpful to know. And the main thing we learned here, the main thing that we used was the phrase time varies inversely with people, so we knew what model to use. Okay, so how long will it take 12 people to complete the job? The same job, 54 hours. 54 hours, alright? Now, sometimes, listen to this, sometimes direct and inverse variation are combined into one problem, okay? So I'm not really viewing this as another type of variation. I'm just saying sometimes they're combined into one problem, okay? Let me give you an example of this, alright? Go ahead and turn your books if you want to page 121, example number 4, and I would definitely write this in your notes so you know where the problem and the information in the notes came from. Feel free to work ahead on the problem. Just make sure you keep one eye up here and check your work as you go. Alright, here we go. Now, a gas law states, hold on one second here, my pen is not working, there we go. A gas law states that the volume of an enclosed gas varies directly, pause, key phrase. So the volume varies directly as the temperature, and the volume varies inversely as the pressure. That'll be interesting, as shown in figure 1.38. So you can kind of look at that if you want to. It's there in your book. The pressure of a gas is 0.75 kilograms per square centimeter when the temperature is 294 Kelvin and the volume is 8,000 cubic centimeters. Model the given information and then find the pressure when the temperature is 300 and the volume is 7,000. Okay, so this looks a little interesting, so kind of bear with me here and let's see if we can't kind of muddle through this a little bit and understand how to do this. Alright, and let's grab a hold of that. There we go, and get us some more space to work with. Alright, now let's start off and read it very carefully. The volume of an enclosed gas varies directly, so the volume varies directly as the temperature. So volume varies directly as the temperature. That's easy, isn't it? Y equals kx, right? Y equals kx. Volume varies directly as the temperature. Then it says, and the volume also varies inversely as the pressure. So now I've got to put the P on the bottom because that's what varies inversely means. Okay? Think about your models, guys. So if it says direct variation, I have that term or that variable right next to K. If it says inversely, then the variable for whatever we're talking about, in this case it's pressure, would go in the denominator. And it's that simple, guys. It is really, really that simple. Okay? So the volume varies directly as the temperature and inversely as the pressure. Now let's go ahead and solve for K. Alright, the pressure of a gas is 0.75, so I'm going to go ahead and put 0.75 for my pressure P. The temperature is 294, so temperature T right here, 294, and I'll go ahead and put K right here. And the volume is 8,000. 6,000. So if I multiply both sides by 0.75, I will get 6,000 equals 294k, or if you want to put the k first, k 294. Alright, now divide both sides by 294, and you're going to get 20.40. 20.40816327. I'm going to round that to 20.41. So there's your k. 20.41 equals k. And of course, if you wanted your answer in fraction, it would be 100. If you reduced it, it'd be 1,000 over 49. But we're just going to go ahead and type 6,000 divided by 294 into our calculators and get out 20.41. Okay, now, so that goes in for k. So here's my final model. Then we can continue on. It says model the given information. So that's what we're doing. V equals 20.41 T over P. There we go. Now I've got a really good model to work with. Okay. And let's go ahead and see if we can answer the last question. It should be pretty simple to do. Just simply substitute numbers in and solve. Model the given information and then find the pressure. So we're looking for P when the temperature is 300. So the temperature is 300. 20.41 times 300. And the volume is 7,000. Go ahead and solve for P. Now obviously I don't want this fraction, so I'm going to multiply both sides by P. So 7,000 P equals 20.41 times 300. Now with my calculator, I'm going to very quickly type in 20.41 times 300, and I'm going to get 6123. 6123. And over here, of course, I still have 7,000 P. Now divide both sides by 7,000. And you're going to get 0.8747. So I'm just going to put pressure equals 0.87. Now the pressure is in kilogram per square centimeter. So it'll be 0.87 kilogram per square centimeters. Okay, 0.87 kilograms per square centimeter. And that would be the answer. Okay, guys. So we modeled it right here after we solved for k and put that number in for k. And then we went ahead and substituted the correct values in for the correct variables and then solved for P. And this is what we get right here. So when the temperature is 300 and the volume is 7,000, the pressure would be 0.87 kilograms per square centimeters. Alright, or cubic centimeters. So, is that right? No, square. Per square centimeters. Okay. Alright, guys, hope this is making sense. Let's go ahead and continue on. Now, let's take a look at joint variation, okay? Copy that down, please, joint variation. Joint variation, guys. And here we go. The model for joint variation is Z equals KXY. So if you'll look, students, it's very, very, very similar to direct variation, only now we have two variables. We still have K, which is a number, it's a constant, and it's still called the constant variation, constant of proportionality, but we no longer have a linear equation here, okay? Actually, I take that back. In most of these cases, we very well could have one, depending on a couple of things, but for now, let's just simply say we have joint variation, okay? And so the model you're going to use is Z equals KXY. Now, having said that, let me tell you when you would use this model. If you see phrases like Z varies jointly with X and Y, or Z is jointly proportional to X and Y, okay? When you see the phrase something varies jointly with something, you know you're going to use this right here. And it might have 3 or 4. It might say Z varies jointly with X, Y, A, and B. Well, if that's the case, then the model would be, okay, you can have as many variables out here as you want when it comes to joint variation, whatever the problem calls for, okay? Now, K is still called the constant variation, it's still called the constant of proportionality. proportionality, so nothing has changed there. Let's apply this to a problem like we've done, alright? So please take some really good notes, and if I go too fast, just pause the video and back it up and go from there, okay? Page 122, example number 5. Page 122, example number 5. Now, students, I would copy this in your notes right here so that you don't have to copy the problem in your notes, okay? And the problem reads as follows. The simple interest for a savings account is jointly proportional to the time and the principal. After 1/4, let's stop right there. So the interest is jointly proportional to time and principal. So let's go ahead and kind of copy this down and see if we can't get a little bit of help with this, okay? The interest is jointly proportional, so interest is jointly proportional to what? Time and principal. There we go. Just like that, I've got the beginning stage of the model up here. Interest is jointly proportional, so equals K, to time and principal TP. Now after 1/4, now hold on a second, guys. The time is supposed to be in years. Now they don't state that in the problem, I'm pretty sure. If I could look back in my book, I don't think they come out and say that, but it is understood that time is in years, okay? So when they say this, now watch, when they say after 1/4, they're giving you the time. 1/4 of a year is 3 months, alright? And so when you go to make that substitution, remember, you're doing it with years, so time would be not 3 months, but 1/4 of a year. You want your time to be in years, okay? The interest is 5,000, so here's I right here. I'm going to put 5,000. Then equals, and then K, alright? The principal, I'm sorry guys, I messed that up, didn't I? I sincerely apologize. It does not say the interest is 5,000. It says the interest on a principal of 5,000 is $43.75. So your interest is $43.75, okay? So the interest on a principal of 5,000 is this. So your principal then is going to be 5,000. There we go. Guys, the only thing left to solve for is K. So very quickly, I'm going to simplify my right side. I can multiply 1/4 times 5,000, okay? And 1/4 times 5,000 would be 1250. And then bring down your K, of course. So I multiplied this times this, and I got 1250. Now divide both sides by 1250, and you're going to get 0.035. Alright, so that would be your K. So I found K. So now all that I have to do is rewrite my beginning model here, and I'll have the final model. So I equals 0.035 TP, and I'm good. I'm erasing this. I've got my final model that I can use. That's really helpful. And so here we go. Now I've modeled this. I've modeled the situation right here. Now let's find the interest after 3/4. So find the interest after 3/4. So 0.035 stays 0.035. It wants 3/4. So my time would be 3/4. And then my principal, of course, would be 5,000 because that's what I'm investing. And see how easy that is, students? It's like a calculator problem. You simply take your calculator and multiply 0.035 times 3/4 times 5,000, and you will get $131.25. That is your interest that you gained. That's the extra money that you have, okay? So there we go, guys. Really, really, really not too difficult, okay? Alright, hopefully this has made sense so far. Let's continue on now, and let's wrap this video up with the study of the least squares formula. You will need your calculators, so go ahead and get them out and turn them on, okay? You will need your calculators. turn to page 123 and look at example number 6. So I'm going to pause while you do that, students. Please turn to page 123 and look at example number 6. Now, I did not type the problem and put it here on the screen in front of you, but if you'll look in your books, it says, right under example number 6, it says, a class of 28 people collected the following data, which represents their heights, X, and their arm spans, Y. So, if you're on the right page, like you're supposed to be, you're going to see this bit of information right here. There it is, okay? So, it looks like they've measured 28 people, and this would be how tall the person is, and this would be their arm span. Now, it must be in inches, I'm guessing. Let's see if it says here. Yeah, inches. And so one person was 60 inches tall, 5 feet, and their arm span, or their wingspan, was 61 inches. So that's what we have as information like that, okay? Now, if you'll look in your book, students, notice also that they have graphed or plotted these points for you right here. So look in your book, and you'll see a scatter plot. Remember a scatter plot from algebra? Scatter plots, they plot all the points. Now, as you can tell, we definitely, please look, guys, we definitely have a linear pattern. I mean, it's definitely not a perfect linear graph, but it's definitely a linear pattern. Now, if the points would have been all over the place, like buckshot, if you've ever gone deer hunting, you know what buckshot is, then no, that's not going to be a linear relationship, okay? But this is definitely has a linear pattern, a linear relationship. So because we can see that, we're going to go ahead and try to find a linear model that best fits this data of information. Now, if I could just show you the least squares regression formula, and maybe I was a little lazy, I don't know. I probably could have Googled it and pulled it up, but it is a wicked, wicked formula. Not wicked as in sinful, okay, but wicked as in terms of it's just really, really long. It takes like every point. So the more points you have, in this case 28 points, it takes every point that you have and it compares it to every other point and the difference in how far apart they are. It's a really, really, really complex formula. And if you have like 4, 5, or 6 points, it takes forever to use the formula. We got 28 points, okay? So the good news is your calculator does this for you, and you are going to need to know how to do this, especially when you get to a stats class in college, okay? You're going to need to know how to enter lists of numbers into your calculator so that you can do different tests or find mean, median, mode, etc. very quickly. So let's get into this right away. I want to show you how to find a linear equation that best represents this scatter plot here, okay? So please take some really, really, really good notes, okay? First, you will want to clear your list out, okay? In other words, on your graphing calculator, there are 6. Most graphing calculators have a place to hold 6 lists. Now, mine's a little older. My nice graphing calculator, Michael has that one, my son, and so I have my old TI-83, but it's pretty similar. It'll definitely work. Now, you don't want to clear your lists out. Maybe some of you are taking a stats class at Chattanooga State. I don't know. Maybe some of you are taking another class there at Berean that requires you to use your lists in your calculator. But if you're not, let's clear out your list so we have no confusion as to what we're doing, okay? And you should be able to know how to do that anyways, because it's always good. It's always good to know how to do that, okay? Just to clear out all your lists. So I'd like you to push a certain button on your calculator, and this will pop up. Now, the button I want you to push, listen carefully, is in the second column from the left, okay? And it's the, no, I'm sorry, students, it's the third column from the left, okay? So, look at the third column from the left, and then go down to the second button from the top, and the button should simply say this, stat. Does everybody see that button? Okay, push that button. Okay, just push that button. And you're going to see this right here pop up on your screen. Everybody see it? Okay, next, scroll down to option 4 and hit enter. Okay, now when you do that, this should pop up on your screen right here. If it didn't, get some help from someone in the class that looks like they know what they're doing, and hopefully that would be at least one person, okay? It should say clear list, okay? Now, you're going to list out your lists. If you will follow my instructions carefully, I will teach you how to do this, okay? So right now your calculator should say clear list, and the cursor or the box should be right here. I want you to go down and look at number 1 on your calculator. So way down at the bottom, you have button number 1, okay? But above that, you should see L1, okay? So I want you to hit shift or second. That's that top left button on your calculator that says second way up here. Hit that and then hit number 1, and this should pop up on your screen, L1, okay? Now, next, you want to hit your comma button. Well, Mr. Error, where's my comma button? Right above the number 7. Everybody look at your calculator, find the number 7, then look right above it, hit enter on that button, and the comma will pop up. Then continue. Look above the button number 2. Above button number 2 is list number 2. So hit second, number 2, and this will pop up. Then hit comma, then hit second, button 3, and L3 will pop up. Does that make sense? Comma. Then you're going to do that for 6 lists. 1, 2, 3, 4, 5, and 6. So if you'll continue doing that process, when you're all done, it should look like this on your screen. Should look like that. L1, comma, L2, comma, L3, comma, L4, comma, L5, comma, L6, comma. Hit enter. Okay, after you've done that, hit enter. And when you hit enter, this should pop up on your screen right here. Oh, I got it backwards. Okay. How did I do that? There we go. It should say done. Okay, so now you know all 6 of your lists are cleared. Now, did you really have to do that? Probably not, but it's good for you guys to know how to clear your lists out of your calculator. Okay, next thing you want to do is the ugly part. You're probably going to have to pause the video and let everyone do this. It'll probably take about 3 or 4 minutes, okay? You have to unfortunately input all of your data. So here's how you do that. Now, it's going to be confusing if you don't listen well. So please listen well. In your book, you have this big array of numbers. See it? Okay. Now, what you're going to do is you first enter all of your x values. So here's x values right here. Here's your x values here. Do you see what I'm doing? Each one of these ordered pairs is an x, comma, y. So here's your x values. Now, it doesn't matter what order you put them into your calculator. I went down, so in my calculator I put in 60, then 75, then 70, 68, then 65, 71, 79, 69, then 68, 62, 69, 70, so on and so forth. Okay, now, Mr. Earhart, that's all fine and dandy. How do you do it? Well, I'm glad that you asked. Here's how you would do this. Okay, watch carefully. What you would do is you would push on your calculator, please, if you would. Clear your screen so your screen's completely clear, and I want you to push again the stat button. Now, if you've forgotten what that is, that's the 3rd column over from the left, 2nd bottom down, 3rd column over from the left, 2nd button down says stat. If you will push the stat button, guys, up will pop this right here on your screen. Now you want to edit your list. In other words, you want to type something in, so hit edit. Okay, so hit enter on number 1, and this should pop up on your screen right here. Something like this. Now you might have a TI 80 something else than I have, but you get the point. It'll look similar to this. Okay, now really, that's not the picture I wanted, guys. I wanted the one that had, sorry about that, it's too late now, I'm already in the video. What you should have on your screen is a dotted line right here, dot, 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 dot. There should be no numbers here. It should be dot, 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 just like this right here. And you can use your arrow button and scroll over to the right, and you'll see it goes all the way up to list 4, list 5, list 6, and they're all totally empty, okay? So what you're going to do now is you're going to enter the data into your computer, or into your calculator. So listen carefully how you do that. So if you scrolled over to the right, I want you to scroll back over to the left now and make sure your cursor is on list number 1. Okay. Now sometimes if you there's no sometimes to it. If you hit up, your cursor is going to be right here on the L1 button. That's not where you want to be. Okay. That's not going to help any. You want to scroll. You don't want your cursor up here. You want to go over to list 1 and then hit the down button so your cursor's right here on this blank. Okay. That's where you want to be. And so, hold on 1 second. My calculator is messing up. Okay, there we go. So make sure your cursor's right hit 60, enter. So go ahead and hit 60, enter. 60 will pop up here. Then hit 75, enter. Well, it's right here in front. I'm not sure why I'm writing. It's right here in front of you. You're going to hit 60, enter, 75, enter, 70, enter, 60, enter, these four numbers right here, then 65, 71, 69, these here, and keep right on going. I'll just scroll down, 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 enter all of the X numbers. When you're done, and go carefully and take your time, then go over here to the L2 column and make sure your cursor's not up here. Make sure your cursor's right down here on the dotted line. Okay, and now you're going to enter all of the what? The Y values, okay? So these are all of your, this is like a table of values, X's and Y. So now you're going to enter 61 like I did here, 61, 74, 70, 67. Then I entered 65, 72, 68, 70, and down it went. So when you've entered all of those, then you have successfully completed the part where you have to enter all of your data. So after you enter all of your X's and all of your Y's, remember, when you get to the end, there should not be more numbers over here than here, or more numbers over here than here. You should have the same amount of numbers here that you have over here. If you don't, then you have the unfortunate dilemma to go back and find the number that you missed and basically start over again, okay? So if y'all want to pause the video, make sure everyone has this information entered, and then continue on, because I'm going to go ahead and continue on now at this time. So if you want to pause the video, make sure everyone has this correctly, and then go on, okay? By the way, once you have this information entered, just hit second quit, and you'll come out of this, and you will not lose your information. It's totally saved, okay? Alright, so there we go. So let's go back a page. First, always clear out your list. It's a good thing to do. Secondly, input all of your data, and we've done that. Lastly, you need to now find the linear equation that fits all of this data that you just entered into your calculator. That is where you use the least squares regression formula, or we also call it the linear regression formula, okay? So here's what I want you to do. I want you to go to your stat button and push stat. And by the way, guys, let me just stop and tell you, once you have your data entered, I mean, there's so much you can do, okay? For example, just ignore the screen. Take your calculator and hit second stat. So your stat button is right here, okay? Here's your stat button. Right above it, it says list. Hit your shift button, then hit stat, and you get a different menu than this. Scroll over to math. Look at all the things you can do with that list, those lists. You can find the minimum number, the maximum number, the mean, the median, the sum of it, product, standard deviation. You scroll down, there's so much you can do. Guys, with this, you can sort them. If you go over to OPS option right in the middle, you should see that. Sorting, delta list would be the change in the list. There's a lot you can do, okay? And so understand that. Now, go ahead and hit second quit. Clear your screen, please. Hit second quit. Now hit your stat button. When you hit stat, this will pop up, okay? Now, next I want you to scroll over to calculate, okay? So scroll over to calculate, and when you do, this screen here should pop up on your calculator menu screen there, okay? And again, look at all the stuff you can do, guys. I mean, you might not know what this means, but you've got one variable stats, two variable stats. If you'll scroll over to tests real quick. Guys, that is all statistics. Z-test, T-test, sample Z-test, sample T-test. I mean, Z-interval. There's so much your calculators will do for you. That's why it's very important you know how to enter your lists into your and look at the very last option under tests. Scroll down. It even does ANOVA. The very last one. And so I'm just telling you guys, when you get to college, use this note. Keep your notebooks. Take really good notes. I've had a lot of students in the past who came to me and said, Mr. Aaron, I kept my math notebooks from Algebra 1, Algebra 2, Pre-Cal, took them to college, and I used them when I could remember how to do certain problems, graph certain problems, or use my calculator, okay? So hopefully you've written really good steps down on how to do all of this. If not, you really should go back and do that so you have hard copy steps, okay? All right, go to calculation and look at that. Students, boys and girls, 1,000. Just kidding, students, men and women. Look at that. Option 4, linear regression. AX plus B. AX plus B. That looks really similar to MX plus B. Well, that's exactly what it is. Only instead of using M for their slope, they use A for the slope. No big deal. So there it is, linear regression. So I want you to scroll down to option number 4 and hit enter. Okay? Scroll down to option number 4 and hit enter. Now when you do that, your screen should say this right here. If I get my calculator to work, my computer to work here, it's about as old as I am. There we go. All right, so it should say this. All right. Now, the next thing you want to do is you want to tell your calculator. I mean, sure, you're telling your calculator you want to use the linear regression formula, but you got to tell your calculator what lists you want to use. So next, this is what you have on your screen. Your cursor should be right here. Here's your little black box right here. You want to hit L1. Remember, that's right above your number 1 button. So hit your shift button, your second button, then hit number 1, and this will pop up. Then hit a comma and hit list number 2. Now it's important you go in that order, guys. If you turn it around, then it's going to think list number 2 was your X's and list number 1 is your Y's, okay? And I know to use these two lists because is that not where I entered my data? Did I not enter my data in list 1 and list 2? Sure I did. So I put L1 here, comma, then L2. So if you do that correctly, your screen should look like this. There it is. Cool. Linear regression, AX plus B, L1, L2. Now hit enter. When you hit enter, this pops up. It tells you what A is and what B is. So, booyah. There you go. Simple. Y equals AX. It gives you everything like this. Y equals AX plus B. So where the A is, I'm going to put 1.006. Because A equals 1.006, then X, and then plus B. Now, you can put plus negative, because B is negative. A positive negative is a negative. So I'm just going to put B is negative 0.225. Okay? Now, hold on 1 second. Clear my screen here. Okay, so that's it, guys. So, that's how you use the linear regression formula, the least squares regression formula, to find a linear equation that best models this information. Now, Mr. Earhart, that's a waste of time. Are you kidding? Are you kidding? I mean, this is the closest formula, the closest linear model you're going to get to that models this data right here. What if you have a business and you have a bunch of data and you can see that it lines up in somewhat of a linear pattern? Well, my goodness, you can get an equation out that you can then use to model future events and to model what could possibly happen. And that can show you a lot of stuff, okay? So it's really helpful, and that is how we do that, okay? All right, I hope this video has been helpful to you guys. If you have any questions, please do not hesitate to call or email.